Okay, some questions we will do. On what factors does the resistance of the conductor depend? Okay, so that means R is equal to rho into L by A. So that means resistance is dependent on resistivity rho and length of the wire and cross sectional area A and also with temperature. So will current flow more easily through a thick wire or a thin wire of the same material when connected to the same source? Why? The current flows more easily through a thick wire than through a thin wire because the resistance of the thick wire is less than that of the thin wire. That means R is directly proportional to L and inversely proportional to A. Okay. If area increase, resistance reduced. So this is the answer. So that means, once again I will tell, the current flows more easily through a thick wire than through a thin wire because the resistance of the thick wire is less than that of the thin wire. Okay. Next, let the resistance of the electrical component remains constant while the potential difference across the two ends of the component decreases to half of its former value. What change will occur in the current through it? So we know that I is equal to V by R. Correct, na? Suppose V dash is equal to V by 2. That means I dash is equal to V dash by R. So which is equal to V by 2R. So which is equal to I by 2. Correct, na? Hence the current through it also becomes half of its previous value. Correct, na? So next, why are the coils of electric toasters and electric iron bars made up of alloy rather than the pure metal? The coils of electric toaster and electric iron bars made up of alloys rather than pure metal because resistivity of alloy is greater than that of metal and it is having a melting point, high melting point. Melting point is high. They don't easily oxidize. Okay. So next, use the data in table 12.2 to answer the following. Which among iron and mercury is better conductor? Just you see, iron is here and mercury is here. It is 10 into 10 to the power of minus 8. So this one is 94 into 10 to the power of minus 8. So iron is a better conductor. And second question, which material is a best conductor? Just you see this table, silver is the best conductor of the least. That means it is having a least resistivity. Resistance are a system of resistors. There are two methods of joining the resistors together. So one is series, another one is parallel. See, take R1, R2, R3 three resistors. This is R1, R2, R3. Join these resistors in series. That means one single line. Okay. So this is said to be a series connection. And same, take same three resistors, connect one above the other. That means parallel each other. Parallel each other. See here, R1, R2, R3. Both are connected to one single point, and other side also one single point. So this connection is said to be parallel. See, one activity 12.4, he is doing or measuring the current. So we are supplying current here through a resistors. Whether you will get the same current in ammeter or not, that he is going to find out here. Join three resistors of different values, that is R1, R2, R3. Connect them with a battery, okay, and ammeter, okay, and a plug key as shown in figure, this one, okay, plug key. You may be use the resistor values 1 ohm, 2 ohm, 3 ohm. So 1 ohm, 2 ohm and 3 ohm. And a battery is 6 volt. Performing this activity, okay, to perform this activity you need 1 ohm, 2 ohm, 3 ohm, etc. and 6 volt battery. Plug the key and note the ammeter reading. Switch on the switch and measure the ammeter reading. Change the position of ammeter. Ammeter you change somewhere, okay, to anywhere in between the resistors. You may put here, I may put here, okay. Note the ammeter reading each time. Whenever you are changing, the here you put. Whenever you changing, note down the ammeter reading each time. Do you find any change in the value of current through the ammeter? So you will observe that the value of current in the ammeter is the same. Wherever you keep this ammeter, you will get a same ammeter reading. So that means independent of its position in the electric circuit, current is independent. So it means that in a series combination of resistors, the current is the same in every part of the circuit, or the same current through each resistor. Okay, same current is measuring throughout the series connection. Okay. So current is same. Wherever you measure, current is same. So by this activity, you will get one clear-cut note on current. So next again 12.5 is doing one more activity. Here what he is doing, potential difference, voltage he is checking. So he is checking voltage. So in activity 12.4, insert a voltmeter across the ends in X and Y. This is X end, this is Y end. Okay, series combination, three resistors as shown in the figure. See, first you measure, you put 1 voltmeter here and you measure the voltage. Plug the key in the circuit and note the voltmeter reading. It gives a parallel difference across the series combination of resistors. So let it be, this is V. Okay. Now measure the potential difference across the two terminals of the battery compared to two values. Okay. Now take out the plug key and disconnect the voltmeter. Now insert the voltmeter across the ends of X and P. This is X and P. This is one resistor R1. So to measure this R1 potential difference, you connect one voltmeter between these 2 points. Okay. Plug the key, measure the potential difference. Let it be V1. This is V1. Similarly, measure the potential. Now you take this to measure the potential across the 2 resistors separately. Let these values be. Again, you connect voltmeter here. Whatever you are getting, that is V2. Same, this is V3. Now, what is the relationship between V1, V2 and V3? So this V is equal to V1 plus V2 plus V3. Sum of potential differences between the 3 resistors is equal to total potential difference. Okay. So you will observe that potential difference V is equal to the sum of potential difference V1, V2, V3. That is the total potential difference across the combination of resistors in series is equal to the sum of potential difference across the individual resistors. That means V is equal to V1 plus V2 plus V3. Okay. Let I be the current through the circuit. The current through each resistor is also I. So it is possible to replace the 3 resistors joined in series by a equivalent single resistor of resistance R such that the potential difference is V across it. So and the current I through the circuit remains the same. Applying Ohm's law. See, we are having one resistor, okay, and one ammeter, and one plug key, and one battery. We are supplying current. Same thing is explaining in these lines. So now apply Ohm's law to it. So V is equal to IR. Correct, na? This is Ohm's law. Now V is equal to what? V is equal to V1 plus V2 plus V3. Correct, na? So V means what? IR. Correct, na? Now we will see what is V1, V2, V3. So we are connecting separate na. Here this is V1, V2, V3. So I is constant, R according to Ohm's law, R1, resistors 1. So current is constant, resistance 2 according to Ohm's law. V3 means I is constant, current is constant throughout the circuit, R3 is resistance. So potential difference between resistance 1 is equal to I into R1, same I into R2, I into R3. Put these values into this equation. So we will get IR1 plus IR2 plus IR3. You take common factor from it. So IR is equal to I common factor R1 plus R2 plus R3. I cancel. So R is equal to what? R1 plus R2 plus R3. So this is the derivation for series connections, resistors in series connections. So we can conclude that when several resistors are joined in series, the resistance of the combination of resistors equal to the sum of their individual resistances R1, R2 and R3. and thus the greater than the any individual resistance.